Here we begin our look at reactions and reactive species, looking first at allylic and benzylic carbocations. So we'll talk a little bit about structure and stability, and then we know that carbocations are important for SN1 reactions, but then when we're done reviewing SN1, we'll also take a quick review of SN2 reactions as well. Last semester, we saw many examples of substitution reactions. Now, if we have an alkyl chloride, that could be a good substrate. Treating this with ethanol. So when we're thinking about substitution versus elimination, ethanol could be kind of categorized as a very, very weak base. So it's not very nucleophilic. It's not going to attack an electrophilic carbon to push away a leaving group, but if a carbocation forms, then it can act as a nucleophile. So the substitution product that will form is this. Now keep in mind how this reaction works. So chlorine can leave, and that will generate this carbocation. And then in a second step, ethanol can attack. It will share its electrons with this carbon, the carbocation carbon, and the next intermediate looks like this. So the oxygen is still connected to the hydrogen and still connected to the CH2CH3 group, but now there is a new bond between the oxygen and the carbon of the T-butyl group. So this oxygen still has a lone pair and it has a positive formal charge. And then in a subsequent step, another molecule of ethanol can act as a base, grab off this proton, allowing these electrons to come back here onto the oxygen, which gives us our final product. This reaction overall is a substitution because chlorine is replaced by the OCH2CH3 group, so this is a way to make an ether. It is nucleophilic because the ethanol acts as a nucleophile, and it is unimolecular because this first step, the formation of the carbocation, this will be the rate determining step. And there's only one molecule involved in the transition state of the rate determining step. So this is an SN1 reaction. Substitution, nucleophilic, unimolecular. Now, what if we look at the same starting material, but this time we treat it with ethoxide? So instead of CH3CH2OH, we're treating it with CH3CH2O-. Again, thinking about substitution versus elimination, ethoxide could be categorized as a strong base. So this is very nucleophilic, and it's too difficult for this to attack here because this group is so crowded. And it's too reactive to just wait for the chlorine to leave. So instead, it is going to grab off a proton, right? So instead of acting as a nucleophile, ethoxide is going to act as a base. So it will grab off a proton from here. These electrons will fold in here to form a double bond, pushing away chlorine as the leaving group. And so we end up with this elimination product. Here's another example, and it's another alkyl chloride treated with ethoxide, and in this case we are going to make the ether. So keep in mind the difference that we're looking at here. This is a tertiary alkyl halide, whereas this one is a primary alkyl halide. We talked about this a lot last semester. For SN1 reactions, tertiary alkyl halides are going to react faster than secondary, and these react much faster than primary or methyl. So these essentially will not undergo SN1 substitution because SN1 substitution requires the formation of a carbocation. So a carbocation is possible with tertiary, also possible, though not as easy, with secondary, but way too difficult with primary or methyl. But SN2 reactions, Methyl halides are going to react faster than primary halides, which are going to react much, much faster than secondary, much, much, much faster than tertiary. So these will essentially not undergo SN2 because they're going to undergo SN1. So it's important to keep in mind what we've seen in terms of SN1 as well as SN2 reactions, to remember the mechanistic details, and to remember the differences in terms of the reaction conditions that will lead to SN1 versus SN2 versus elimination. Let's continue to look at SN1 substitutions. Here we again have a tertiary alkyl chloride. We're treating it with ethanol, and we get SN1 substitution leading to the ethyl ether as the product. Here we also have a tertiary alkyl halide, and when this is treated with ethanol, you will get the related product. But the difference is when we think about the relative rate. So if we call this a rate of 1, then the second reaction proceeds 123 times faster. Why is that? Well, look again, and what we notice is that this is not just a tertiary halide, it is tertiary and allylic, right? So we have our alkene, and then the adjacent position, this is the allylic position, and so here we have an allylic chloride. So this one is tertiary and allylic. So there must be something special about a tertiary and allylic carbocation that makes it easier to form than just a tertiary carbocation. So let's take a look at that. Now, when the chlorine leaves, then we get this carbocation, which is tertiary, which looks very similar to what we saw above, except if you look carefully, you'll notice that we can draw another resonance structure. So I'm using a dotted arrow to represent the imaginary movement of electrons when we're talking about resonance, and we can draw another resonance contributor that looks like this. In the first resonance structure, our carbocation is tertiary. In the second example, our carbocation is primary, but it's still primary and allylic, so it is a reasonable carbocation. Now, because we have resonance, that is going to significantly stabilize this carbocation relative to the tertiary carbocation that's formed here. So keep in mind when we're talking about resonance structures, neither of these exist. What exists is going to be the resonance hybrid, which is going to look something like this, with a partial positive here and a partial positive here. So because that partial positive is spread out, that helps to stabilize the carbocation intermediate. Over here, we have an electrostatic potential map, and blue is positive. Red is negative, blue is positive in these electrostatic potential maps. And so you can see that we have a buildup of positive charge here as well as here. Now, when we think about an allylic carbocation, why is resonance possible? Well, the hybridization of this carbon is sp2, this carbon is sp2, and this carbon is sp2, which means in addition to the sp2 orbitals, we have a p orbital, another p orbital, and another p orbital. So we have 2 electrons that can be spread out over 3 pi orbitals. Now let's take a look at one more example. This is another solvolysis reaction. I didn't have the numbers for ethanol again, so this one is solvolysis in water. Again, we're talking about an SN1 substitution, and here we have a tertiary alkyl chloride, which is converted to a tertiary alcohol, and this has a relative rate of 1. And in our other example, this one is tertiary and benzylic. Chlorine is connected to the benzylic position, so this is tertiary and benzylic, and this will undergo substitution. And this one proceeds at a rate that is 600 times faster. Once again, what we see is that tertiary and benzylic, just like tertiary and allylic, there's something special about that. So let's think about the carbocation that can form. So when chlorine leaves, we get this intermediate, but we can draw another resonance structure. So let's imagine that these electrons move here, and that gives us another resonance contributor that looks like this. And then we can imagine these electrons move here, giving us another resonance contributor that looks like this. You can imagine these electrons move here, giving us another resonance contributor. Where are we? That looks like this. And then finally, we can imagine these electrons move here, which gives us a resonance contributor that looks like this. In other words, this particular benzylic and tertiary carbocation exists as the resonance hybrid, which has partial double bond character here and partial double bond character all around the ring. There is a partial positive charge at the benzylic position and at both ortho positions and at the para position. So the positive charge is highly delocalized, right? It's really spread out over all of the carbons because there is so much resonance. And again, if we look at the electrostatic potential map, we have positive character here, as well as the ortho positions and the para position. All right, so that positive charge is spread out because we have this extended pi system. And whenever we have delocalization of electrons, whenever we can spread out charge, that is going to make the species much more stable. All right, so this is what's special about allylic and benzylic systems, is the possibility of resonance. So when we have allylic and benzylic carbocations, we are talking about resonance structures, and so the resonance hybrid is more stable than a comparable non-allylic or non-benzylic carbocation. Now here is another example of SN1 substitution of an allylic chloride. And what we observe is that in addition to the expected product, we also get a mixture that includes a different product. Right? How does this happen? Well, again, let's think about the mechanism. And chlorine leaves, and we get this carbocation. And remember, we have another resonance structure that looks like this. So remember, neither of these resonance contributors exist. What exists is the resonance hybrid that has double bond character and partial positive character here and partial positive character here. To be more specific, we would predict that this would be the major contributor because this carbocation is tertiary and allylic, whereas this carbocation, if it existed, is primary and allylic. So this one would be more stable, so this is the major contributor, which means our resonance hybrid is going to look a little bit more like this one. So in other words, we are going to have more partial plus character at the tertiary position and a smaller partial plus at the primary position. Now, we have water. This is our nucleophile, and the nucleophile can add to this position or to this position. All right, that's why we end up with a mixture of products. Right? And it's actually easier to see it when we're thinking about the resonance contributors, right? Even though these don't exist, it is helpful to look at it this way when we are trying to keep track of our electrons, right? So if we think about water adding here, that's going to add there, and that gives us this, which then leads to this, which is the first product. On the other hand, if water adds here, that gives us OH2 plus, and then that's going to lead to this product. The good news is because of resonance, reactions that go through allylic carbocations can be a lot faster because the allylic carbocation is more stable than comparable non-allylic carbocations. But the bad news is because of resonance, there is the possibility of reaction happening at different positions, which would lead to a mixture of products. So that's something you have to be on the lookout for when you have reactions that involve allylic carbocations. Now, when we looked at this reaction of a benzylic chloride, though, we saw that this product was formed. Okay, was I just skipping details? Do we get a mixture? No, this is the only product that's formed. Why don't we get a mixture here? Because, again, we can think about chlorine leaves and we get this intermediate, and then we get this resonance contributor and other resonance contributors as well. But let's just look at these first two resonance contributors. So if water adds to this position, and then I'm skipping the proton transfer step, right? So we get this, which is aromatic. On the other hand, if water added to this position, and then we had a proton transfer, then we would end up with this, which is no longer aromatic. All right, so aromatic compounds are so special that to lose aromaticity when you have the option to be able to keep aromaticity, this is going to proceed to a negligible amount, right? So we get essentially 99.9999999% of this, and you probably can't even find any products that would result from attack at either of the ortho positions or the para position, because that involves the permanent loss of aromaticity. With the resonance structures, we have kind of a temporary loss of aromaticity in our intermediate, but our final product, aromaticity, is restored. So with allylic systems, you do have to watch out for the possibility of what's called an allylic rearrangement, but that same thing does not happen with benzylic systems. Let's talk briefly about SN2 reactions. Now remember, SN2 reactions are concerted, so we're not talking about carbocations, but I just wanted to mention them here because we were reviewing SN1, so we might as well review SN2. Here we have a primary alkyl halide, and when we treat this with a strong base such as methoxide, remember this is going to attack here, kicking out bromine as a leaving group, and that gives us OCH3. So this is a concerted reaction, SN2 substitution nucleophilic bimolecular, because there are two molecules in the transition state of the rate determining step, right? There's only one step. If we look at the next example, this one is primary and allylic. And so again, this will do SN2 substitution, leading to this product. And the third example, this one is primary and benzylic. So an analogous reaction, this will give us the methoxide. Now up on the top right, we have this substrate is secondary and allylic, but we're treating it with a strong base. So secondary alkyl halide plus a strong base is going to lead to E2 elimination, right? So the same thing with allylic systems as with non-allylic systems. A secondary alkyl halide will lead to elimination, not substitution, when treated with a strong base. And this one is secondary and benzylic, but once again, we're going to get elimination, not substitution, because it's secondary. Okay, so we still have to remember the rules that we learned last semester. A methyl or a primary alkyl halide will undergo SN2 substitution with a strong base or a weak base. A secondary alkyl halide will undergo elimination with a strong base, SN2 substitution with a weak base, and SN1 substitution with a very, very weak base. And then tertiary alkyl halides will undergo E2 elimination with a strong base, E2 elimination with a weak base, SN1 substitution with a very, very weak base. All right. If we're talking about primary, secondary, tertiary, and allylic or benzylic, it follows the same rules that we saw last semester. All right. So let's use what we learned and let's predict what we're going to get. Okay. So this compound, the alkyl halide, is secondary and allylic. And cyanide is not as strong as an alkoxide, so we can put this in our weaker base category. So secondary and a weak base, this is going to give SN2 substitution. So we get this product by SN2. Now for this compound over here, we have a tertiary and benzylic bromide, and we want to do substitution. So remember, if we treated it with methoxide, this is a very strong base, so this is going to lead to elimination, not substitution. So instead, we want to treat it with methanol. We want to use a very, very weak base so that it will undergo SN1 substitution. So that takes care of a little recap of SN1 as well as SN2 reactions. And we also saw what's special about allylic and benzylic carbocations.